Hi, my name is Chase Martin, and my partner is Monis Khan, and we are Group 7. Our final project features automating fairness and bias testing in machine learning models using synthetic data generation and explainability metrics. The first section of this presentation will introduce you to our topic. The rise of machine learning and artificial intelligence systems has revolutionized decision-making processes across integral fields within modern society, such as healthcare, finance, hiring, and criminal justice. By automating complex predictions and analysis, machine learning models offer significant advantages, such as improved efficiency and scalability. However, these models are also prone to inherent risks, as they can inadvertently learn and perpetuate biases present in the data or embedded within algorithms, leading to unfair or discriminatory outcomes. The implications of such algorithmic biases can be particularly severe in high-stakes applications, where decisions directly impact lives, worsening societal inequalities. As a result, ensuring fairness and mitigating bias in machine learning systems has emerged as a priority in the artificial intelligence and research community. Fairness in machine learning is a multifaceted concept, often analyzed through group fairness and individual fairness patterns. Group fairness measures evaluate whether a model treats specific demographic groups equitably, using metrics such as demographic parity, which requires decisions to be independent of protected attributes, and equalize odds, which mandates equal false positive and negative rates across groups. On the other hand, individual fairness ensures that similar individuals receive similar outcomes, regardless of their membership in different demographic groups. These fairness definitions highlight the challenge of achieving universal standards, as optimizing one metric may conflict with the others due to trade-offs inherent in fairness evaluation. Despite the extensive research on fairness definitions and metrics, ensuring fairness in machine learning models remains a challenge due to limitations in the current testing frameworks. Traditional software testing methods primarily focus on functional correctness and system performance, often overlooking fairness and ethical concerns. Toolkits like IBM AI Fairness 360 and Microsoft FairLearn provide mechanisms to compute various fairness metrics and apply debiasing algorithms. However, these tools largely rely on evaluating static datasets, limiting their ability to detect inherent biases that emerge in dynamic, real-world scenarios. Similarly, platforms like Akitas and Verify Machine Learning add fairness checks but often depend on manual slicing and lack automated mechanisms for testing scenarios involving underrepresented groups. Addressing these limitations requires frameworks that integrate advanced methodologies to uncover and mitigate hidden biases. One of the most innovative and interesting methods to mitigate bias in machine learning and AI models is the use of synthetic data generation techniques, which enhance fairness testing by making datasets more robust with artificial samples that represent underrepresented groups or simulate counterfactual scenarios. Techniques like the synthetic minority oversampling technique, or SMOTE, rebalance datasets by generating synthetic instances of minority groups, while generative adversarial networks, or GANs, can create highly realistic data that mimics real-world distributions. In addition to this, counterfactual data generation supports fairness testing by creating paired samples that differ only in sensitive attributes, allowing an evaluation of whether model decisions change solely due to protected characteristics. These methods allow researchers to achieve comprehensive testing coverage, exposing biases that may remain undetected in skewed or incomplete training datasets. To complement the synthetic data generation, the use of explainable AI techniques provides insight into inner workings of machine learning models. Explainable AI methods such as Shapley Additive Explanations, or SHAP, and Local Interpretable Model Agnostic Explanations, or LIME, independently dissect the decision-making process of complex models to identify the contributions of individual features to predictions. For example, SHAP values decompose fairness metrics like disparate impact into feature-level contributions, revealing whether models rely on sensitive factors like socioeconomic indicators such as zip codes that drive biased outcomes. Similarly, LIME provides local insights into individual predictions, allowing researchers to examine how feature importance shifts between counterfactual instances. This interpretability ensures not only the detection of bias patterns, but also provides actionable guidance for model refinement and removal of sensitive proxies. Despite the progress in fairness testing and explainability, most existing fairness frameworks do not integrate synthetic data generation interpretability into an automated framework. The lack of solutions in this area of machine learning and AI necessitates a robust solution that combines advancements in fairness metrics, synthetic data generation, and explainability techniques. The proposed framework extends the current state of fairness testing by addressing its key limitations. By leveraging synthetic data generation, the framework ensures robust coverage of underrepresented groups and facilitates counterfactual checks to reveal biases. Additionally, the use of SHAP and LIME adds interpretive depth, pinpointing specific features that contribute to biased decisions and providing clear recommendations for improving model fairness. The integration represents a scalable approach, aligning fairness testing with the broader goals of developing responsible, transparent, and trustworthy AI and machine learning systems. This paper's contributions include three primary advancements: automated workflows for generating synthetic data sets tailored for fairness evaluation; 2. Integrating of multiple fairness metrics to evaluate both original and synthetic data for bias; and 3. Adoption of explainable AI techniques to diagnose and interpret the root cause of bias outcomes. These contributions aim to fill existing gaps in fairness testing methodologies, while offering a flexible and scalable solution applicable across domains such as healthcare, finance, and hiring. In showcasing the framework on a case study using UCI adult income dataset, this research highlights its ability to uncover deeper disparities than existing fairness toolkits, while providing comprehensive explanations to inform ethical AI development. The next section of this presentation will consist of a literature review reviewing past work on our specific topic. Fairness in machine learning has been widely studied, with formal definitions and metrics developed to quantify bias. Two common group fairness metrics are demographic parity and equalized odds. Demographic parity requires the model outcomes be independent of protected attributes such as gender or race. For example, a hiring model should select candidates at equal rates across genders. This is often measured using metrics like statistical parity difference or disparate impact, which aim to ensure no group is systematically favored in positive outcomes. Equalized odds is a stricter definition, demanding that the model's true positive rate and false positive rate are equal for all groups. This ensures that the model performs equally well for each demographic, addressing not just the allocation of opportunities but the quality of service for different groups. However, these fairness metrics can be mutually incompatible, meaning optimizing for one may conflict with the other. For instance, achieving demographic parity may reduce accuracy or violate equalized odds. Choosing the right metric depends on the context, such as legal standards or domain ethics. This multiplicity of fairness definitions is a key challenge, as there is no one-size-fits-all solution, and ensuring fairness often involves trade-offs between these criteria and overall model accuracy. To address the challenges of fairness in machine learning, several frameworks and toolkits have emerged to help practitioners evaluate and mitigate bias. IBM AI Fairness 360 is an open-source library offering a comprehensive set of fairness metrics such as disparate impact ratio, statistical parity difference, and equal opportunity difference. It also provides algorithms for bias mitigation through pre-processing, in-processing, and post-processing techniques. Microsoft FairLearn is another toolkit that includes assessment dashboards for parity metrics and mitigation algorithms. Tools like Akitas and Verify Machine Learning offer fairness audits and fairness unit tests for models, allowing users to specify protected attributes like race and gender and compute metrics comparing model performance across subgroups. A common test is the disparity test, which checks if a performance metric of one group differs significantly from another. For example, the 80% rule or 4/5 rule flags a model as biased if an unprivileged group's positive outcome rate is less than 80% of the privileged group's rate. While these tools are valuable, they have limitations. They generally evaluate bias on a given dataset and do not automatically generate new scenarios or data. This means that they might miss biases that arise from underrepresented groups or a rare feature combination. Additionally, they focus more on the metrics and less on explaining the root causes of bias in the model's logic. Synthetic data generation has emerged as a promising approach to address data bias and limited coverage issues in fairness testing. By creating artificial data that mimics real-world distributions, synthetic data can introduce more diversity or balance into datasets without the need of costly new data collection. Techniques like SMOT or GANS are commonly used for this purpose. For example, oversampling minority groups with realistic synthetic examples can counteract underrepresentation, leading to fairer model outcomes. Unlike undersampling, which discards information, synthetic data augmentation preserves the original data while improving fairness. Another approach is counterfactual data generation, where for each individual, a counterpart is created with a certain sensitive attribute change, like flipping gender. This allows us to test how the model's predictions differ, directly evaluating individual fairness. Studies such as those on the UCI adult census data set have shown that the synthetic data can produce bias in income predictions while improving key performance metrics. However, challenges remain, such as ensuring synthetic samples are realistic and cover meaningful feature combinations. Poorly generated data can introduce noise or unrealistic cases, leading to false assumptions about model bias. Overall, synthetic data allows us to stress test models on a broad spectrum of conditions, including balanced demographics, edge cases, and rare attribute combinations, going beyond the limitations of the original dataset. Explainability plays a critical role in understanding and addressing fairness in machine learning models. Explainable AI techniques like LIME and SHAP are widely used to interpret complex black box models. LIME provides local linear approximations of models' behavior around a specific prediction, highlighting which features influence the outcome. SHAP measures each feature's contribution to a prediction based on cooperative game theory, offering a consistent way to explain model decisions. Recent work has applied explainable AI to fairness auditing. For example, SHAP values can decompose a fairness metric like demographic disparity into contributions from each feature. This helps identify which factors are responsible for bias. In one case study, SHAP revealed that a late payment feature was driving higher risk predictions for one group, highlighting it as a cause for disparity. Similarly, LIME can generate per instance explanations, allowing us to check if changing a sensitive attribute like gender significantly alters the model's prediction rationale. Despite these advances, most existing fairness toolkits do not deeply integrate explainability. This is a gap and an opportunity. Combining fairness metrics with explanation methods not only flags bias but also helps understand its root cause. Such insights are crucial for practitioners to justify and correct fairness issues, such as removing or transforming problematic features. The next section of the presentation will walk you through the experiment conducted.
Coming on to approach, our approach has three key stages. The first one is synthetic data generation. We over sample minority groups, example as mode, or flip protected attributes to create counterfactual pairs, ensuring we test the model under balanced and what if conditions. The second stage is fairness metrics. We compute standard measures like disparate impact, demographic parity, difference, and equalized odds on both the original and the synthetic sets. If, for instance, disparate impact drops below 0.8, it flags potential bias. The third one is explainability. We then use SHAP and LIME to see why a bias occurs, pinpointing features or proxies that are driving unfair predictions. By integrating these steps in a single pipeline, we expose biases that stay hidden in a skewed dataset while also providing actionable insights on how to address them. Now let's discuss how we actually implement this framework. We use Python because it offers a rich ecosystem of libraries: scikit-learn for standard model building, AIF 360, or fairlearn for calculating fairness metrics, and SHAPs or LIME for interpretability. In practice, our workflow looks like: first, we load or train a baseline model on the original dataset. Second, we generate synthetic datasets, rather balanced or with counterfactual flips of the protected attribute. Third, we run fairness metrics to check for disparate impact or demographic parity differences. And fourth, we apply SHAPs or LIME so that if the metrics indicate biases, we know which features are likely driving it. This pipeline is mostly automated. Each time we update the model or gather new data, the same script rechecks fairness and produces both metrics and explanation results. The goal is to make sure fairness testing becomes as routine as performance testing, so that biases don't slip into production models unnoticed. Coming on to extended results and analysis. Here's what we found using the UCI audit income dataset as a test bed. First, the data's original distribution was skewed about 70% male and 30% female. When we rebalanced by oversampling female data, we saw a slight drop in overall accuracy from roughly 0.85 to 0.83 in logistic regression, but an improvement in the recall for female instances. Checking fairness metrics, we noticed a bigger disparity. That disparate impact metric fall below the 0.8 threshold. Once we considered the balanced or counterfactual scenarios, this shows that while the model might have looked fine on paper with the original test set, it actually exhibits deeper bias against female examples. Conclude Confusion metrics also confirm that many positive outcomes for females were being missed, indicating more false negatives. In other words, oversampling highlighted exactly where the model was understanding female success rates, and that's critical for fair decision making. Bias can be even more pronounced at the intersection of multiple attributes like race and gender. So we also briefly examined intersectional fairness. For instance, a model might not just be biased against women, but specifically against non-white women, creating double disadvantage. We also found it is helpful to calculate confidence intervals for our fairness metrics, especially if the synthetic sets are small. This tells us how stable or uncertain our measures are. If the interval around a metric crosses an important threshold, it means we should interpret the bias flag with caution and maybe gather more data. Finally, we compared our pipeline to existing tools like IBM, AIF 360, and Microsoft Fairlearn. They are excellent for computing fairness metrics on a given dataset, but they don't automatically generate new synthetic or counterfactual examples. As a result, they might miss biases that only surface under balanced or flipped conditions. Our integrated approach uncovers these hidden issues more reliably. Coming to evaluation and comparisons. Summarizing all the evaluation results performance. The first one is performance balancing. Generally reveals deeper biases but can slightly reduce accuracy. This trade-off might be worth it if our main goal is ethical fairness rather than raw performance. The second one is fairness metrics. On balanced or counterfactual sets, we consistently observed disparate impact dropping below 0.8, a clear indicator of bias. Third, conclusion metrics affirmed that female examples were receiving more false negatives. Compared to the standard fairness toolkits, our pipeline not only flags bias but also uses synthetic augmentation to actively search for those blind spots. This combination of data augmentation, metrics, and interpretability provides a more complete picture on how unfairness arises in the model. Now let's go over the performance and fairness results. Here we see how our approach affects both performance and metrics. Fairness for two models, logistic regression and random forest. On the left, notice how accuracy and record slightly drop when we move from the original data to the balanced set. This is the trade-off of focusing on minority groups. At the same time, we check two key fairness measures, which are disparate impact DI and demographic parity DP difference. For the original set, DI stays around 0.82 to 0.84, suggesting less obvious bias. But once we balance or create counterfactual examples, DI falls to around 0.64 to 0.66, well below the 0.8 threshold. This flags a more serious bias that was hidden in the skewed data. Likewise, DP difference roughly doubles from about 0.1 up to 0.2, plus showing a bigger gap in positive predictions for the protected group. Overall, this table confirms that simply evaluating on the original imbalanced dataset can underestimate a model's bias. Adding synthetic data uncovers deeper disparities in how the model treats male versus female examples.
This next section will conclude the presentation, recapping information and talking about future work. To conclude, our research introduced an automated fairness framework that combines synthetic data generation, fairness metrics, and explainable AI to detect and diagnose bias in machine learning models. By generating synthetic data through techniques like oversampling and counterfactual scenarios, we were able to uncover hidden biases in underrepresented groups that traditional methods might miss. We evaluated multiple fairness metrics, such as disparate impact and equalized odds, on both original and synthetic datasets, revealing disparities that were not apparent in the original data. Additionally, we integrated explainable AI tools such as SHAP and LIME to interpret biased outcomes, providing actionable insights into the root causes of unfair predictions. Our case study on the UCI adult income dataset demonstrated the effectiveness of this approach, uncovering deeper gender biases that were otherwise hidden. This highlights the importance of systemic fairness testing and ensuring equitable outcomes in AI systems. Looking ahead, there are several exciting directions for our future work. First, we plan to integrate advanced generative models such as GANs and causal generators to create more realistic synthetic data that better reflects real-world distributions. Second, we aim to incorporate additional fairness metrics, including intersectional fairness and counterfactual fairness, to evaluate bias across multiple dimensions. Third, we will establish continuous integration practices to monitor and mitigate bias as data and models evolve over time. Fourth, we plan to develop user-friendly dashboards and visual reports to make fairness testing accessible to non-technical stakeholders. Finally, we aim to scale this framework to more complex models and larger datasets across diverse domains, such as healthcare and criminal justice. By embedding automated fairness tests into the machine learning pipeline and leveraging explainability for root cause analysis, we hope to promote the development of more responsible, transparent, and trustworthy AI systems that deliver equitable outcomes for all.